Every hose, every valve, every liter of water on this truck is placed exactly where it is for a reason, and that reason was calculated in advance. To understand the scale, think about a modern pumper truck like the Pierce Enforcer. It weighs over 20 metric tons, fully loaded. Its onboard pump can move up to 2,000 gallons of water per minute. That's enough to fill a standard swimming pool in under 4 minutes. It carries hundreds of meters of hose in pre-connected lines, a built-in foam system, hydraulic rescue tools, and enough personnel equipment for a full crew. And it has to be ready to operate within seconds of arriving on scene. By common sense, managing that much machinery under that much pressure should require a team of specialists and hours of setup, but engineering says otherwise. And everything you see on a modern fire truck is the result of over a century of design, failed systems, and relentless refinement. The origins go back further than most people expect. In the 17th century, the first fire engines were nothing more than hand-operated pumps mounted on wheeled carts. Teams of men worked levers back and forth to push water through a single hose. It was slow, exhausting, and barely effective. In the 18th century, horse-drawn engines improved response times dramatically. Then, in 1841, the first steam-powered pumper was built in New York. It could push far more water than any hand pump, but early firefighters, threatened by the technology, sabotaged it. The machine was withdrawn. But the principle was proven, and the need for it was undeniable. After that, progress accelerated. Steam gave way to internal combustion engines. Wood gave way to welded steel. And somewhere along the way, engineers stopped designing vehicles that simply carried water and started building systems that could control, pressurize, and deliver it with surgical precision under the most extreme conditions imaginable. But despite all the innovation, the core principle never changed. A fire truck is always about one thing: getting water onto fire faster and more effectively than anything else on the road. So how does a vehicle with a fixed water tank actually fight a building fire that might burn for hours? The answer lies in two systems that work together from the moment the truck stops. The first is the onboard tank. Every pumper truck carries between 500 and 3,000 liters of water, depending on the vehicle type. This is not the primary water supply. It is the initial attack supply. The moment the crew arrives, the pump operator engages the pump from inside the cab, connects the tank to the pump discharge, and charges the pre-connected hose lines. Within seconds of stopping, water is already flowing. No setup, no waiting. That immediate water supply is what allows the first attack to begin before a hydrant connection is ever established. Those first seconds matter more than most people realize. In a structure fire, conditions can change completely within 2 minutes. The onboard tank buys the crew the time they need to establish a permanent supply without losing the initiative. The second is the centrifugal pump. This is the mechanical heart of every pumper truck. Water enters the pump through an inlet, flows into the center of a rapidly spinning impeller, and is flung outward through the impeller vanes into a volute casing. That rotational energy converts directly into pressure. The faster the impeller spins, the higher the pressure. A modern fire pump can generate between 150 and 250 pounds per square inch under normal operating conditions. At that pressure, a hose line can project a solid water stream over 30 meters, enough to reach the upper floors of a mid-rise building from street level. But the onboard tank alone is never sufficient for a prolonged fire. That's where the hydrant connection enters the picture. And this is where a common misconception needs to be cleared up right away. A fire truck does not simply connect to a hydrant and let city water pressure do the work. City water mains typically operate at 60 to 80 pounds per square inch. That is nowhere near enough pressure to supply multiple attack lines simultaneously. The fire truck's pump takes the incoming hydrant pressure, adds to it mechanically, and delivers it to the hoses at the pressure required. The pump is not a relay, it is an amplifier. The pump operator manages this process from the pump panel, a control board mounted on the side of the truck. Every discharge valve, every pressure gauge, every incoming supply is controlled and monitored from this panel. When a second hose line is opened, pressure across the system drops. The operator increases throttle, which increases impeller speed, which restores pressure. When a line is shut down, pressure rises. The operator compensates. This constant real-time management of pressure and flow is what keeps water arriving at the correct force at every nozzle simultaneously. It is not automated. It is a skilled operation performed under extreme time pressure by a trained pump operator. The hose system itself is more complex than it appears. Lines are pre-connected and stored in the hose bed in specific configurations. Larger diameter supply lines, sometimes 10 centimeters across, carry water from the hydrant to the truck at high volume. Smaller attack lines, typically 4 to 5 centimeters in diameter, carry pressurized water from the truck to the firefighters at the door. Each hose type is matched to a specific flow rate and nozzle pressure. A fog nozzle on an attack line requires around 100 pounds per square inch at the tip to produce an effective spray pattern. A smoothbore nozzle works best at 50 to 80 pounds per square inch. Getting the wrong pressure to the wrong nozzle means less effective suppression at exactly the moment it matters most. Every hose on the truck is stored in a specific location for a specific reason. The pre-connected attack lines sit closest to the cab, ready to be pulled immediately. The longer supply lines sit toward the rear, deployed last. Foam concentrate is stored adjacent to the pump panel, so the operator can introduce it into the water stream without leaving the panel. Breathing apparatus is mounted at shoulder height on the side of the truck, so a firefighter moving toward the building can grab it without breaking stride. Nothing on a fire truck is placed for convenience. Everything is placed for sequence. The layout of the vehicle is itself a choreography, designed so that a crew of 4 can execute a full deployment without a single unnecessary movement. Then there is the aerial ladder. On a ladder truck, this is an entirely separate hydraulic system mounted on the vehicle's chassis. Before the ladder can be raised, 4 outriggers extend from the sides of the truck and anchor it to the ground. These stabilizers redistribute the vehicle's weight over a much wider footprint. Without them, a fully extended ladder carrying a crew member and water weight would tip the truck. Once the outriggers are deployed and locked, a hydraulic pump pressurizes fluid through a system of cylinders. One set of cylinders elevates the ladder. A second set extends the telescoping sections. A hydraulic motor rotates the entire assembly left and right. The operator controls all of this from a joystick panel at the base of the ladder. Modern aerial ladders extend to over 30 meters. At full extension, they can deliver water from an elevated master stream nozzle through a pipe that runs the full length of the ladder. Load sensors, angle sensors, and hydraulic interlocks prevent overextension or unsafe operation automatically. The system does not allow an operator to exceed the ladder's rated capacity, regardless of what controls are activated. That is not a software override. It is a hard mechanical limit built into the hydraulic circuit itself. If the load sensor detects too much weight at too great an extension, the hydraulic valve closes. The ladder stops. The operator cannot override it from the controls. Safety is not a setting. It is a physical constraint engineered into the machine. There is one final detail that most people never consider. The positioning of the truck itself is part of the system. Aerial ladder trucks cannot operate directly against a building. They need a specific distance, typically between 3 and 10 meters, to achieve the correct extension angle for the ladder to reach upper floors safely. Pump operators need to be close enough to the hydrant to avoid excessive pressure loss through long supply lines, but far enough from the structure to avoid falling debris. The driver who positions the truck at a fire is not simply parking. They are making a set of engineering decisions in real time that will determine what the vehicle can and cannot do for the entire duration of the incident. Every time you watch a fire truck arrive on scene, it looks like controlled chaos. Crew members moving in every direction, hoses being pulled, ladders going up, water appearing almost instantly, but it is not chaos at all. It is a system executing a sequence that has been calculated, drilled, and refined over decades. The pump, the hose system, the aerial ladder, the hydrant connection, every component supports the others. If one water supply runs low, another takes over. If one hose line needs more pressure, the operator compensates at the panel. If access is blocked at ground level, the aerial goes up. To me, that is what makes the fire truck extraordinary. Not the size, not the sirens, the fact that every single capability on that vehicle exists to solve a specific problem that the last version couldn't.